Sorry guys, my phone just kind of died out on me. Okay, so my goal is to find or derive how I got that equation up at the top. So if I drew a free body diagram for the car on a flat curve, I know that the car would have a weight force. And then I also have, if I'm thinking about, it's a great car, I know. Here's my car. It has a weight force. The road is going to push up on the car, so it has a normal force. And then it's moving around, let's call that the curve. It's going to be moving then toward or around that curve, so what's keeping it, oh, I'm sorry, totally just messed up where my dot was. Okay, weight force down, ground's pushing back up on it, so there's my normal force, and it's the force of friction that's keeping it along that curve. So my friction force is going to be directed in that horizontal direction. Okay, so this would be my free body diagram for a car that's going around a flat curve. And this would be at any given point as that car is maneuvering or negotiating a curve. So if that's my free body diagram, I just want to write some of the forces. We could do a sum of the forces in the y. We could think about a sum of the forces in the x. Okay, so if I did the sum of the forces in the y, then that would give me n minus mg equals 0. It's not accelerating in that vertical direction, so n equals mg. Okay, that really doesn't do me any good for this up here. So if I do the sum of the forces in the x direction, that would give me static friction is equal to my centripetal force, because it's accelerating then around that flat curve in the horizontal direction. So that would be mv squared over r. Okay, but let's simplify this. Static friction is equal to mu s times the normal. That equals mv squared over r. Let's simplify that down, because I know that the normal is equal to mg. So I could say mu s times mg equals mv squared over r. Let me simplify this down even more. Mass on both sides, let me cancel that. So now I get mu s times g equals v squared over r. So now if I rearrange this for v, I would get v equals the square root of mu s times g times r. So all we did was just use Newton's second law to derive that my speed on a flat curve, if I'm in a car, is equal to the square root of the coefficient of static friction times the acceleration due to gravity times then the radius of how far my car is then to the center of that circle. Okay, so all we did was prove it. Okay, on this question, it says a 1,500 kilogram car moving on a flat horizontal road negotiates a curve as shown on the previous slide. We just saw how we derive speed. It says if the radius of the curve is 35 meters and the coefficient of static friction between the tires and the drive payment is 0.523, find the maximum speed of the car. Find the maximum speed that the car can have and still make the turn successfully. We just found an equation for calculating maximum speed. And that maximum speed was v equals coefficient of static friction times the acceleration due to gravity times the radius then. And everything they gave me in this problem, they gave me mass, they gave me radius, they gave me the coefficient of static friction. So I didn't even need the mass. All I needed are these two pieces, and if we did just plug them into the equation that we just derived, I'm going to take the square root of 35 times 0.523 times 9.8, and then you should get like around 13, okay? So if you did this problem though for me on an FRQ, or if you did this problem for me on homework, you would have to derive the equation. You can't just write the equation down and say, yeah, this is what I know, that's how I know I find maximum speed. It doesn't work that way. You're gonna have to go back and do all of the work that we did here. So I have to do all of this, then I can plug in my numbers to find that maximum speed, okay? So we'll continue on with the banked roadway, which is really just you negotiating a curve, but now it's at an angle. And we'll do that part on Monday. You have some homework questions. That I also will post on your blog. So you have these and then a few problems. And have a really wonderful weekend. And I'll see you Monday.